Hello everyone. So we are back after a long time, and today we will be starting with a new series for us. We will be looking at learning reverse engineering and binary analysis topics further on. But before we get into those, we have to make sure that our assembly language basics are good. So to do that, we will be starting with the assembly language first. And today's session, we will be covering some basic terminologies, the basic architecture, basic registers, and all the basic necessary information that we need to get started. Okay. So first, we will start with understanding the basic architecture of the processor. So processor or CPU is the brain of the computer, and an internal clock synchronizes and controls all the processor's operations. The basic unit is the clock cycle, which is rated in terms of megahertz. So megahertz is like a million cycles per second, and one cycle is hertz. So here in front of us we have the basic architecture of a processor. So as you can see, the this CPU is mainly divided into two parts here, and this part is the execution unit, and this is the bus interface unit. So purpose of the execution unit is to execute the instructions, and the bus interface unit delivers the instructions and data to the execution unit. So execution unit contains the arithmetic and logic unit, control unit, and a number of registers. The most important function of the the bus interface unit is to manage the bus control unit, segment registers, and instruction queue. So bus control unit controls the buses that transfer the data to the execution unit, as well as to the memory and to input output devices, whereas the segment registers control memory addressing, and the BIU, the bus interface unit, also accesses instructions from memory and places them in the instruction queue uh, for the execution unit to use. So let's have a look at the evolution of microprocessors. So previously, in the initial days, the 8088 microprocessor was introduced by Intel, and it had 16-bit registers and 8-bit data bus. So using the 16-bit registers, 8-bit data bus, and a 20-bit address bus, it was possible for this processor to address up to 1 million bytes of internal memory. So this 1 million bytes, it is dependent upon the 20-bit address bus size. So if you just calculate 2 raised to the power of 20, it comes to 1 million bytes. And 1 million bytes is like approximately 1 megabyte. So although the registers can process 2 bytes at a time. So if you see here, it is a 16-bit register, so it will be processing 2 bytes at a time. The data bus, which is the 8-bit data bus, can only transfer 1 byte at a time. This processor runs in what is called the real mode, in which only one program runs at a time. with actual real addresses in the segment registers. So after the 8088, there came the 8086, in which the only difference was the upgraded data bus. So data bus was also 16-bit in this processor. So after the 8086, Intel introduced 80286, which definitely runs faster than the preceding processor and has additional capabilities. So this processor can address up to 16 million bytes. So how it does this is with the 24-bit address bus. That is why it is able to now access addresses up to 16 million bytes. So 16 million bytes, again, it will be like 16 MB. So this processor and its successors can operate in real mode as well as protected mode. So like what is this real mode and protected mode? We will get into it in maybe next slide. And because of these new features, it was possible for the operating system to do multitasking. So once we have understood about real and protected mode, we will have a clear understanding that why was this not possible in the previous architectures and why is it possible in this newer one. So after the 286, Intel introduced the 80386. So this one has 32-bit registers and 32-bit data bus, and it can address up to 4 billion bytes. So 4 billion bytes, it comes approximately to 4 gigabytes of memory, and it supports protected mode as mentioned previously. And along with protected mode, this processor also supports something called virtual mode. So in virtual mode, it is possible for the processor to swap portions of memory onto the disk. In this way, programs running concurrently can have space to operate. So after the 80386, we have the 80486. So this one also has 32-bit registers and a 32-bit data bus. So along with those, a high-speed cache memory was introduced in this processor. This cache memory was connected to the processor bus, enabling the processor to store copies of the most recently used instructions as well as data. So after the 486, we have the Pentium. This also has the 32-bit registers but a 64-bit data bus, and it has separate caches for data and for memory. So after the Pentium, there came the Pentium 2 and 3. So they have dual independent bus design that provides separate paths to the system cache and to the memory cache. So these processors are connected to the built-in storage cache by a 64-bit wide bus. So after the Pentium 2 and 3, we have the Pentium 4 with some more new additional features. So in this processor, we had a new cache subsystem with two level of cache with a 128 byte cache line size, and execution cache was provided for storing decoded instructions, and hence it was possible for the processor to remove the decoder time latency from the execution loop. So Intel in this processor has also introduced their NetBurst microarchitecture SIMD streaming SIMD extensions 2 SSE 2 technology. So SIMD is single instruction multiple data for higher speed and performance. So processors up beyond 80486 have what is called as a single stage pipeline, which restricts them to completing one instruction before starting the next one. So pipelining involves the way a processor divides an instruction into sequential steps using different resources. So before the 486, okay, not after, before the 486, all these processors had this single stage pipeline. So the processors that came after Pentium, even the Pentium and after Pentium, it had like a five-stage pipeline. Sorry, the Pentium had the five-stage pipeline architecture, and the ones that came later than that had even the better ones. So let's try to understand what is real mode and protected mode in the context of the processors. So real mode is something that was there in 8088, 8086 processor. So older processors uh, supported these. So these processors have 20-bit address bus. As we had seen in the previous slide, they had a 20-bit address bus, and so they were able to store addresses up to 2 raised to 20, that is 1 megabyte. So real mode provides direct access to the hardware RAM and unrestricted memory access. There is no mechanism provided in real mode to protect memory regions and preventing processes from overwriting each other's memory. This mode does not support multitasking due to hardware lacked memory protection. For the protected mode, so this is a more advanced operational mode. It was made for the x86 processors and introduced with the 80286 as we had seen it previously. So it supports 32-bit addressing, enabling access up to 4 gigabytes of memory. So 2 raised to 32 if you see. So with the address bus of size 32, we can access up to 4 gigabytes of memory. So segmentation in protected mode is an advanced memory management technique that expands on the concepts used in the real mode. While in real mode, segmentation is primarily used to extend addressable memory space beyond 64 KB by dividing memory into 64 KB segments. Protected mode introduces protection to these segments. Every segment in the protected mode has a set of permissions and properties that we need to set in order for in the data structure that is called GDT. So every time uh, the segment has to be accessed by a process, it has to have the necessary permission set in the GDT so that it is able to access. And because of this, it was possible to work with multiple processes at a single time in protected mode. So now we will talk about addressing data in memory. So there are two methods we can do for addressing data in memory. First is the absolute address, and second is the segment offset. So in absolute address, like it is supported by the real mode processors 8086, 8088. So let's say a memory with a location 05A25H is a 20-bit value that directly references a specific location in the memory. So it is a real address in the memory, and it is how the absolute address works. And in the segment offset address, it combines the starting address of a segment with an offset value. So in the upcoming sections, we will see how this segment offset works. So segments and addressing. So segments are the special areas that are defined in a program for containing the code, and it can also contain data and the stack, as you can see here in the diagram. So there are different segments for different purposes in a code. Also, you can have any number of segments to address a particular segment. So in a code, you can have multiple segments of the same type. So while you are addressing these segments, which are like, maybe two or three segments could be there in the code segment itself. And when you want to address these segments, you will only change the base pointer of that address. So in real mode, three main segments are code, data, and stack. In code segment, it contains machine instructions that are to be executed. For data segments, it contains programs, defined data, constants, and work areas. For stack segment, it contains any data and addresses that the program needs to temporarily have for our own subroutines or any procedures that our program requires. In protected mode, these segment register contain a selector address which is used to find the segment base address from the descriptor table that we had just discussed a couple minutes back. So this address is used along with the 32-bit offset to find the exact address. As you can see in the diagram, this is how a typical program would look in the memory. And these values that you see here, code, data, stack, and extra, these will be the addresses of the segments in the memory. So again, the addresses that will be contained in these will depend upon of what processor is it. It can either be an absolute address or a segment offset address. Coming to segment registers now, in 8086 or 8088, the segment registers of these processors are 16 bits in length and operate only in real mode. And talking about the individual registers itself, the CS registers. So this register contains the selector of program's code segment. So code segment's address will be stored in this one. And this gets the segment's base address plus an offset value in the instruction pointer, indicating the address of the instruction that is to be fetched for execution. In DS register, it contains the selector of a program's data segment. So instructions use this address to locate the data. This address plus an offset value in an instruction causes a reference to specific byte location in the data segment. The SS register, it is used for implementing stack in memory. The system stores the starting address of a program's stack segment in the SS register. So this segment address plus an offset value in the stack pointer, the SP register, indicates the current word in the stack being addressed. The ES register, it is used by some string operations to handle memory addressing. And also we have the FS and GS register. So these are additional extra segment registers which were introduced in 80386 for handling storage requirements. So this is all we had discussed about specifically about segment registers. Then we have one more set of pointer registers. So pointer registers are the 32-bit EIP, ESP, EBP registers. So let's have a look at function of the purpose of each of these registers. So IP register, it is instruction pointer register. The 16-bit IP register contains the offset address of the next instruction that is to be executed. So IP is associated with the CS register in that IP indicates the current instruction within the currently executing code segment. Normally we don't have a reference to the IP in a program, but we can change its value. Like when we are debugging a program or something, we have control to change values in these registers. Then we have the stack pointer register. So this is also a 16-bit stack pointer register. It provides an offset value which when associated with the stack segment register refers to the current word being processed on the stack. Then we have the BP register. It is the base pointer register. This the processor, this is also a 16-bit register. The processor combines the address of this pointer with the stack segment, with the address in the stack segment, with the offset in the base pointer. So base pointer can also be combined with uh, DI and SI. I think we have them ahead with the index registers, data index and the stack index for various operations. Then we have these general purpose registers. So general purpose registers are the 32-bit EAX, EBX, ECX and EDX. So in these 32-bit registers, as you can see here, they can be divided into 2 or 3 parts. So for example, in the first one we have EAX. So AX is the rightmost 16 bits of the EAX. So this is the entire AX register, and inside of the AX register itself there will be two parts, AH and AL. So AH will be the high and AL will be the lower part. So both of them will be the 8 bits. And this feature we can individually address any portion of the register by providing the target address. Talking about the AX register, AX is the primary accumulator and it is used for operations involving input, output and most arithmetic operations. So it is typically like we can use it for multiply, divide, addition. Then we have this BX register. So it is also known as the base register. Again, the same, it is EX and it will have different parts like BH, BL, and the second entire part called BX. The same way we can address as we had discussed for AX, and it is the only general purpose register that can be used as an index to extend addressing. Another common purpose for BX is for computations. BX can also be combined with the data index and source index as a base register for special addressing. The CX register, the CX also is known as count register. So it may contain a value to control the number of times a loop is repeated, or to, or like, to check if the value shifts bits left or to the right. It is also possible that we can use for computations this ECX register. Then we have the DX register. Some input output operations require its use, and multiply divide operations that that have large values also use this DX and AX together. Then we have the index registers. So index registers are the 32-bit ESI and EDI. Again, the rightmost portion, 16-bit portion, are the stack, the SI and the DI. The SI register, the 16-bit source index register, is required for some string or a string character or for handling operations. And in our context, so this is associated with the DS register, the data segment register. For the DI register, it is the destination index register. It is also required for string operations. In our context, DI is associated with the ES register, referenced as EDI. Then we have the flag registers, and the 32-bit flag register contains the bits that indicate the status of various activities. So many instructions involving comparisons and arithmetic change and comparison and arithmetic change the status of the flags, which some instruction may test to determine subsequent actions that are to be performed. So different flag registers that we have here are the OF, like the overflow flag. So it indicates overflow of a high order bit after the arithmetic. Then we have the direction flag, which determines left or right direction of moving for comparing or to move the data. Then we have IF, interrupt flag. It indicates all the external interrupts such as keyboard entries or mouse clicks. Then we have the trap flag. So this permits operation of the processor in a single step mode. So normally debug programs will use this flag. Then we have the sign flag, which contains the resulting sign of an arithmetic operation. So if it's 0, it is a positive, and if it's 1, it's negative. Then we have zero flag, ZF, which indicates the result of an arithmetic comparison. We have AF as auxiliary carry, so which contains a carry out of 3 bit into bit 4 in an arithmetic operation. Then we have the parity flag, which indicates the number of 1 bits that result from an operation. So it can be either even or odd parity. And we also have carry flag. So it contains carries from high order bit following an arithmetic operation. So this is it for today, and I hope we have a basic understanding now of the different types of registers, the basic architecture of the CPU, and what is the basic purpose of these different types of registers. So in the upcoming videos, we will be working on some programs and using these registers for writing some code. So uh, the purposes that we have discussed today, the registers that we have discussed today, we will be using them in the upcoming videos to to run some sort of code using them. So that's all for today. Thanks for watching.